So for this proof we need some preliminaries. So what for that purpose we will need to use the Banach fixed point theorem, and these are some preliminaries for that purpose. So we need the notion of a normed vector space. So vector space V is called normed if to each vector V in the vector space capital V there is a real valued function which we will call as the norm, and we will denote it as the norm of V by this notation, such that this norm is always greater than or equal to 0. So the norm of a vector V will be a real number and it cannot be negative, that is what it says. Moreover, so this is greater than or equal to 0 for all V, and also it is equal to 0 only for the vector V equal to 0. This is the first condition required from the norm function. Another condition that is required is if we scale the vector V by a constant alpha, then the norm also gets scaled by that same number alpha, the same number alpha if alpha is positive, and absolute value of alpha in general. So for any real number alpha and a vector V, this equality has to be satisfied. And finally the triangular inequality is required to be satisfied. So for two vectors V1 and V2, the norm of V1 plus V2 cannot be more than norm of V1 plus norm of V2. This triangular inequality is also required to be satisfied for all vectors V1 and V2. So this is called triangular inequality. This is called the linearity property of the norm function, and this is the definition that the notion of length of a vector is required to satisfy. In the context of convergence, we also need what is the definition of a Cauchy sequence. So in the context of convergence, we like to say that elements in a sequence are going close to each other. So in general, if elements in a sequence A n go close to each other, do they converge to some element A? So the answer is in general no. Just because elements A n are converging close to each other does not mean they will eventually converge to a number A. So this, if it does converge, then we will call the sequence convergent. In order to arrive at that, we will define this property called Cauchy. So a sequence A n is called Cauchy if for every epsilon greater than 0 there exists some capital N, possibly depending on epsilon, such that if we want that A n and A m are smaller than epsilon, then that will be satisfied for all n and m that are greater than this capital N. So the importance of this statement is, it says that elements A m and A n are going close to each other. If you want them to be close to each other, closer than a number epsilon, then all we have to do is take m and n greater than some capital N. So when somebody specifies a epsilon greater than 0, we are able to find number n such that this inequality is satisfied for all n and m greater than capital N. So in general, if epsilon is made smaller, then capital N might have to be made larger. So this quantifies, this makes precise the notion that elements in the sequence A n are going closer and closer to each other. So every convergence sequence is Cauchy, but it turns out that the converse is not true. So if a sequence is Cauchy, it just means that elements are going close to each other, but it does not imply that there is a number A to which it converges. So if we assume an important property called completeness, then we will also be able to guarantee convergence. So what is the definition of completeness? So if a sequence is Cauchy, then completeness would guarantee that there exists a number A such that A n converges to A, and this latter convergence is what we will say convergent in the usual sense. So this is what we will use for the definition of complete of a normed vector space. A normed vector space V is called complete if every Cauchy sequence is convergent. Convergent in the sense of this limit. So we see that if every Cauchy sequence, in other words a sequence in which all elements are going closer and closer to each other, if we are going to say that it converges to a number in that particular set, in that particular vector space V, then this vector space V is going to be called complete. Finally, a complete normed vector space is called a Banach space. So, what is a Banach space? It is a normed vector space which is also complete. In other words, every Cauchy convergence sequence is also convergent. Some examples of complete spaces: a set of real numbers R, this is by definition of R, this is complete. Rn is also complete, where n is some finite number. So, if we take n tuples of real numbers, then this is also a complete vector space. So, which norm here, it turns out, is not relevant. Yeah, we could take, for example, the standard Euclidean norm. We could take the Euclidean norm, which is very standard. Suppose a vector V is in Rn, then we can define, this is one of the definitions, V1 square plus V2 square plus Vn square. This guarantees that it is positive, and when we take square root, it is also linear in V. So, this is one of the norms of Rn. What is Rn? It is a n tuple. Every element in Rn is an n tuple in which n is finite. So, this is one definition of norm, and this is called the 2 norm. It is also called the Euclidean norm. We could also have taken V, so called the infinity norm, as the maximum for I equal to 1 up to n of the absolute value of the ith component. V1 up to Vn, there are n components in the vector V. For each of those vectors we take the absolute value, and for each of the components we take the absolute value, and we look at the maximum for I varying from 1 to n of this absolute value. That is called the infinity norm. So, we will see some more notions of norm. So, with respect to any of the norms, it turns out that Rn is complete. What are examples of incomplete spaces? So, the set Q of rational numbers, this is incomplete. What is rational? Q is a standard notation for the set of rational numbers. Any number q, small q, in this capital Q can be written as the ratio of two integers z1 by z2. So, if a number q can be written as ratio of two integers, then q is said to be a rational number, and capital Q is a set of all such rational numbers. So, it turns out that q is not complete. For example, pi and square root of 2, these are some numbers which can be approximated arbitrarily well using rational numbers. To be able to approximate arbitrarily well, for example, we know that square root of 2 can have a decimal expansion. If we take more number of digits in the decimal expansion, then we get a more accurate representation of the number square root of 2, and similarly for pi. But just because we can approximate square root of 2 and pi by a very good approximation using decimal expansions, that does not imply that there are integers z1 and z2 such that z1 by z2 is equal to either pi or square root of 2. In fact, there do not exist z1 and z2 such that z1 by z2 is equal to pi. Similarly, there do not exist integers z1 and z2 such that z1 by z2 is equal to square root of 2. In other words, pi and square root of 2 are so called irrational numbers. However, we know that these irrational numbers can be approximated arbitrarily well. This proves that Q is not complete. Another important set, another important space that is complete is the so called space of continuous functions on this interval 0 to delta, where delta is strictly greater than 0 with respect to the sup norm. With respect to the sup norm, it turns out that this space of continuous functions is complete. So, the space of continuous functions on this interval, functions from this interval to Rn, is also denoted by C, by this notation. Yeah? So, the 0 here means that it is just continuous, differentiability is not being guaranteed. So, I should emphasize that it is important that with respect to the sup norm only, C0, this one is complete. There could be some other norms with respect to which it is complete, but here it is no longer the case that the norm is not relevant. Which norm we are taking, that will very crucially decide whether this space of continuous functions is complete or not. That statement depends on the norm with respect to which we are asking the question. The space of continuous functions from the interval 0 to delta to Rn. These are functions which are not necessarily differentiable, but they are just continuous, and hence 0 has been put here. They take the domain is from 0 to delta, it takes its values, time varies from 0 to delta, and for each time instant in this interval it gives a vector in Rn. So, this is the space of continuous functions from this interval to Rn, and we are saying sup norm. What is a sup norm? If f is an element of this set, then the sup norm we are going to define as the maximum when t varies from 0 to delta of f of t. So, at each time instant f of t is an element of Rn. Yeah, this is the meaning of f is an element of continuous functions from this interval to Rn. So, at each time instant t, this is some vector, and for that vector we defined already the Euclidean norm, the 2 norm, and this 2 norm is defined for each time t in this interval, and we will look at the maximum of this particular function as t varies from 0 to delta. This maximum is said to be the sup norm of the function f. So, sup norm is no longer relevant to a particular time instant, even though f of t 2 norm was relevant to which time instant the 2 norm was being taken. So, the sup norm is a norm on the space of continuous functions from this interval to Rn. So, with respect to this sup norm, it turns out that this is a complete space, but with respect to which norm is it not complete? For example, we can also define the so called L2 norm. So, what is the L2 norm? For the same space of functions, we can define f L2 norm as integral from 0 to delta of So, we can take the 2 norm of the vector f of t at a time instant t, and the 2 norm we take the square and we integrate from 0 to delta. Upon integrating from 0 to delta, we get some number that is no longer dependent on the time t, and its square root is said to be the L2 norm of the function f, where f is an element of this. So, this L2 norm also is no longer dependent on t, but f of t before we took the 2 norm here is indeed a function of time t, but after we integrate from 0 to delta, this is no longer dependent on time t. So, this is the L2 norm. So, with respect to L2 norm, this same space of functions is not complete. Just because elements are going very close to each other does not mean that it will also converge to a function that is continuous and close to each other. For that, we are using the notion of L2 norm. So, with respect to the sup norm, however, two functions, if they are going close to each other, they will eventually converge to a continuous function again inside the space. So, finally, using these notions, we can state the Banach fixed point theorem. So, for that we just need the notion of a closed subset and a contractive mapping. So, for a set X, a subset S of X is said to be a closed subset of X if the boundary of S is within X. This is how we understand a closed subset. More precisely, S is a closed subset of X if and only if elements of X which are arbitrarily close to S are also within S. If we take an element of X which is very close to elements of S, which is close to one or more elements of S, then it is not necessary that this elements of X should also be within S, but if it is indeed within S, then S is said to be a closed subset of the set X. And what is contractive? So, if X is a normed vector space, a map P from X to X is said to be contractive if there exists a number rho that is strictly less than 1, such that this inequality is satisfied for all x1, x2 in X. What is this inequality? Px1 minus px2 is at most rho times x1 minus x2. So, what is the importance of this inequality? X1 minus x2 can be interpreted as a vector from x2 to x1, and px2 to px1 is the vector upon action under P. So, this vector is getting contracted under the action of P. Why contraction? Because this rho is some number strictly less than 1. So, we will say this map is contractive if there exists such a number rho such that this inequality is satisfied for all x1 and x2 in X. The number rho should not have to be modified depending on which x1 and x2 we take in capital X. For such a map P, we will say it is contractive if such a number rho exists. So, we are ready to state the Banach fixed point theorem using the notions we have just now defined. So, let X be a Banach space and let S be a closed subset of X, and then let T, a map from S to S, let T be contractive. Then first of all, there exists a unique fixed point X star in S, fixed point for this operator T. Moreover, that fixed point X star can be found quite easily. What is easily? It can be found by successively operating T on any x1 in S. We take any x1, then we take T times x1, then we take T times T of x1. When we do this iteration, we will converge to that unique fixed point. We will use this Banach fixed point theorem for the proof of the existence and uniqueness theorem of the solution to the differential equation in the next lecture. Thank you.